Hello and welcome students to this lecture of our book Electrodynamics. Today we will discuss about the parallel plane waveguide. Okay, so this is the topic for today's discussion: the parallel plane waveguide. Although this is the very first lecture in this mode, that is in the online mode, and some problem may arise to in this mode, but we can discuss about these problem and try to solve them. But for the time being and for the situation being, this is the best method or best way to teach you or to send you some strategy about your syllabus, about your topics. So that's it. So the today's topic is parallel plane waveguide. Firstly, we have to discuss what is a parallel plane waveguide. Okay, so look here that what is a parallel plane waveguide. So let us consider a parallel plane waveguide which have two parallel plates. The plates are infinite in one direction, say in y direction, and is separated by a distance in x direction. The direction of propagation of EM waves is in the positive z direction. Say look this figure. इस फिगर में आप ये देख पा रहे हो कि हमारे पास ये दो पैरेलल प्लेट्स हैं, ठीक है। इनको आप पैरेलल प्लेन्स भी बोल सकते हैं, आप इनको पैरेलल प्लेट्स भी बोल सकते हैं। सो इस तरह का ये जो कंस्ट्रक्शन है, इस तरह का कंस्ट्रक्शन है कि ये जो पैरेलल प्लेट्स आपको दिखाई दे रही हैं, ये एक एक्सिस पे इनफाइनाइट एक्सटेंट की है और दूसरे एक्सिस पे किसी एक डेफिनेट डिस्टेंस से सेपरेटेड है। सो हमने कंसीडर किया है ऊपर दैट प्लेट्स आर इनफाइनाइट इन वन डायरेक्शन, से इन वाई डायरेक्शन। ओके, तो इस डायरेक्शन में जो डायरेक्शन ऑफ वाई एक्सिस है, हमने इन प्लेट का जो एक्सटेंशन है वो इनफाइनाइट मान लिया है, और ये एक्स एक्सिस की डायरेक्शन में, इस एक्सिस की डायरेक्शन में ये प्लेट्स एक दूसरे से स्मॉल ए डिस्टेंस से डिस्टेंटेड है, सेपरेटेड है। एंड द electromagnetic wave propagate in positive direction, positive z axis direction, that is propagate in this direction, this. So this is the situation for the parallel plane waveguide. It means आप ये सीधा समझ सकते हैं कि एक parallel plane waveguide कुछ इस तरह से हमारे पास वर्क करेगी। जो हमारे पास, मान लीजिए हमारे पास इस तरह का एक parallel plane waveguide है, ठीक है, और ये एक परफेक्ट कंडक्टर से कुछ इस तरह से बना हुआ है, कुछ इस तरह से परफेक्ट कंडक्टर है। और आप ये जानते हैं कि टोटल इंटरनल रिफ्लेक्शन की फिनोमिना होती है। तो वेवगाइड जब ये दो पैरेलल प्लेट हैं, दो एक दूसरे से जो है वो कितनी डिस्टेंटेड है, ए डिस्टेंस, एंड दिस द डायरेक्शन ऑफ जेड एक्सिस, this is direction of x-axis, and this is the direction of y-axis. So the total internal reflection की फिनोमिना होगी कुछ इस तरह से, कुछ इस तरह से ये वेव इस वेव गाइड में, जिसको हम पैरेलल प्लेन वेव गाइड कह रहे हैं, इस तरह से आगे बढ़ती जाए ड्यू टू द फिनोमिना ऑफ internal reflection, total internal reflection. Okay, so this is so. For this, as we consider the plates are extended to infinity in the positive y direction. So the field due to the field will be constant in this direction and of y-axis, or we can say that there will be no change in the fields in this particular direction. हमने माना है कि जो y एक्सिस की डायरेक्शन में है वो इन प्लेट्स का जो एक्सटेंशन है वो इनफाइनाइट है, तो उस डायरेक्शन में जो फील्ड होगा वो इनफाइनाइट एक्सटेंट का फील्ड होगा। और अगर उसका रेट ऑफ चेंज हम देखें, उसका रेट ऑफ चेंज ऑफ दैट पर्टिकुलर फील्ड, और हमने कहा कि उस डायरेक्शन में फील्ड कांस्टेंट होगा, तो अगर उसका डेल बाय डेल वाई ऑफ ए कांस्टेंट निकालें आप, और कांस्टेंट कौन है इस समय? कांस्टेंट इस समय है आपके पास फील्ड इन दैट पर्टिकुलर डायरेक्शन, field in that particular direction. So del by del y of a constant is always be 0. That's why this del by del y is equals to 0. So putting this result into equation number 8, first maybe your equation number is different from my equation number, so that is not the matter of discussion. So if you put this result, del over del y is equals to 0, you get that? कहाँ से आया है? बिकॉज हमने ये माना है एज वी कंसिडर द प्लेट्स आर एक्सटेंडेड टू द इंफिनिटी इन द वाई डायरेक्शन, सो फील्ड विल बी constant in that direction of y-axis, or we can say that there will be no change in the fields in that particular direction. So change with respect to y is always 0. Change with respect to y direction is always 0. So putting this result into our equation number, and my equation number is this is my equation number. So I put this result here, and this is the equation number 8, and this is the equation number 8 first, that is del 2 over del x square plus del 2y del y square plus omega by c square minus k square Ez equal to 0, and the same equation for the Bz. You know that very well that what are Ez and Bz. Ez is the longitudinal electric field, that is the field into the direction of propagation of EM waves, and Bz is the longitudinal magnetic field, that is the field into the direction of propagation of EM waves. So put the result del by del y is equals to 0 in this equation. Okay, what we can get that see here, what we can get from this is this, that if we put del by del y equals to 0 in that particular equation, then we can get del 2 Ez over del x square plus omega by c square minus k square Ez equals to 0, because this factor del 2 by del y square is 0. So we are left with del 2 by del x square plus omega by c square whole square minus k square Ez equals to 0. This is the differential equation. So we are left with this differential equation, del 2 Ez over del x square plus omega by c square whole square minus k square Ez equals to 0. And for the sake of our calculation, अपनी कैलकुलेशन को हम आसान बनाने के लिए हम ये मान रहे हैं कि ये जो फैक्टर है जो ब्रैकेट में लिखा है, that is omega by c whole square minus k square, say this is beta square. Okay, so this is beta square. तो आप ऐसा कंसिडर करते हैं, तो जो हमारी जो इक्वेशन है, इक्वेशन नंबर ए हम इसे कह रहे हैं, जो हमने ये रिजल्ट पुट किया है, तो ये वाली जो इक्वेशन हमारे पास डिफरेंशियल इक्वेशन है वो किस तरह से हो जाएगा, दैट del 2 Ez over del x square, the same factor here, and omega by c whole square minus k square, this factor is equals to beta square. So put beta square in place of the bracketed factor. So we are left with that plus del 2 Ez over del x square, this plus beta square Ez equals to 1, and say this equation number 9. Okay, this is my equation number, and maybe your equation number is different, but that is as I said earlier, that is not the point of discussion. Okay, so now take a look of the solution of the above differential equation can be written as, कैसे लिखा जा सकता है, Ez, which is the function of x and z, is equals to a sin beta x plus b cos beta x. और इस तरह की जितनी भी डिफरेंशियल इक्वेशंस हैं, उस तरह से आप इस तरह की डिफरेंशियल इक्वेशंस को पहले भी सॉल्व करते आए हैं. किस तरह से सॉल्व करते आए हैं कि अगर आपके पास इस तरह का कोई डिफरेंशियल इक्वेशन कि d2x by dx स्क्वायर प्लस 4 d2x by dt square, and this is 4x equal to 0, and say this is m square plus 4 is equals to 0. So m square is equals to minus 4, m is equals to minus 4 I square plus 4I square m square, and m is equals to plus minus 2I. So we can write that solution of this type of differential equation is x equals to a sine 2x plus b cos 2x. Simply this. So this is the method. This is the one method. There are many possible methods to solve this type of differential equation, but this is the one of them to solving this type of differential equation. So we have this type of differential equation, that is del 2 Ez, where Ez is a function of x and z, that is a function of position, plus beta square Ez equals to 0. So this is equation number 1, and solution we can write easily as Ez xz, Ez which is a function of xz equals to a is a constant, any positive constant, sine beta x, because here in place of any number, that is say in this example we can see that in place of beta square we have a number 4. Okay, so this is not the problem. So the solution of this type of differential equation can be written as that Ez, which is a function of x and z, is equals to a sine beta x, plus b again a constant, cos beta x. Say this is equation number 10. And in the same way we can write the we can obtain the solution of the longitudinal magnetic field, और इसी रिजल्ट को, that is del over del y equals to 0 वाले रिजल्ट को अगर हम फिर से इस इक्वेशन में पुट करें, that is our equation number 8 second, that is del 2 over del x square plus del 2 over del y square plus omega by c whole square minus k square equal to bz, and put that result, that is del over del y equals to 0 here. So this term will be 0. So we are left with del 2 bz over del x square plus omega by c whole square minus k square bz equals to 0. So this. So solution of that type of differential equation we can write in the same fashion as we write the electric, that is the longitudinal electric field, and in the same fashion we can write the longitudinal magnetic field Bz, which is again a function of x and z, that is the function of position, is equals to c is again any constant, and sine beta x plus d cos beta x, a replaced by c, any other positive constant, sine beta x plus b replaced by d, and cos beta x, the same factor. So this is equation number 11. So now we get the solution of the two differential equation with this constraints, that del over del y is equals to 0. And why this happened? Because field into the direction of y-axis we consider as a constant, and the partial differential with respect to y of a constant is always be 0. So with this constraint we get the longitudinal electric field and longitudinal magnetic field given by equation number 10 and equation number 11. So now we will discuss about the different modes of propagation of EM wave. Different mode of propagation of EM wave. The first one is the TEM mode, that is the transverse electric mode. The transverse electric mode of propagation of EM waves. The transverse electric means the field transverse to the direction of propagation can only be held, and the field which is into the direction of propagation of EM waves definitely be vanished. Okay, so this The TEM mode of propagation is a mode in which electric and magnetic fields are transverse to the direction of propagation of EM waves, and there will be no longitudinal fields present. Okay, so in TEM mode, Ez is definitely equals to 0 and Bz is also be 0. ठीक है, जब भी आप TEM मोड ऑफ प्रोपेगेशन के बारे में डिस्कस करेंगे तो हमेशा वहां एक कंडीशन होगी कि जो सस्टेनेबल फील्ड होंगे वो केवल ट्रांसवर्स डायरेक्शन में हो सकते हैं, लेकिन ऐसा नहीं होगा हमेशा वहां की कोई भी, अगर आप इस मोड के बारे में डिस्कस कर रहे हैं, दैट इज द TEM मोड ऑफ प्रोपेगेशन, की वहां कोई लॉन्गिट्यूडनल फील्ड सस्टेन कर जाए, इट इज नॉट पॉसिबल इन द केस. सो in TEM mode of propagation, the longitudinal electric field and longitudinal magnetic field definitely be 0. Okay, so by putting these results into equation number 7, we can get the transverse fields, and we have equation number 7 as this. This is the equation number 7, and we have here the transverse field, the value of Ex given by this type of equation, value of Ey given by this type of equation, and value of Bx given by this type of equation, and value of By given by this type of equation, and these all is considered as equation number 7, and these are the transverse electric and magnetic field components. These are all transverse to the direction of propagation of EM wave. So why these fields are called as or known as the transverse electric and magnetic field components. So when you put this result that Ez equals to 0 and Bz equals to 0 into this equation number 7, you can easily see here, put Ez and Bz both are 0. So when you put Ez equals to 0, you get 0 here. Bz equal to 0, you get 0, and 0 is multiplied by this factor, then Ex is definitely be 0. See the result for Ey. If Ez equals to 0, this term will be 0. If Bz equals to 0, this term will be 0. So the whole term, bracketed term will be 0, and bracketed term multiplied by this factor will definitely be 0. So now in the same way we can get the result for Bx, the transverse electric, the transverse magnetic field or magnetic field component into the direction of x-axis. So Bz 0, Ez 0, term bracketed term will be 0, so Bx will be 0, Bz 0, Ez 0, so this term will be 0, and By is definitely be 0. So you can see here that if the longitudinal electric and longitudinal magnetic fields are 0, then the transverse electric and magnetic field will definitely be 0. So in this mode of propagation, which is known as the TEM, the transverse electric magnetic mode of propagation, if Ez equals to 0 and Bz equals to 0, then by putting these results into equation number 7, and we see now this is the equation number 7, which gives you the transverse electric and magnetic fields component. So the rest component, that is the transverse electric and transverse magnetic field components, will be 0 due to this result, that is for the TEM mode. So all the field components vanishes, and thus in a parallel plane waveguide does not support the TEM mode of propagation of EM wave. बिल्कुल क्लियरली ये बात है कि अगर आपके पास किसी भी प्रकार का कोई भी फील्ड कंपोनेंट प्रोपेगेट नहीं कर सकता, ना तो आपके पास लॉन्गिट्यूड इलेक्ट्रिक फील्ड है, ना आपके पास लॉन्गिट्यूड मैग्नेटिक फील्ड है, ना आपके पास ट्रांसवर्स इलेक्ट्रिक फील्ड है, ना आपके पास ट्रांसवर्स मैग्नेटिक फील्ड है, तो फिर प्रोपेगेट क्या करेगा? there will be no propagation. So in the conclusion sense, we can say that this mode of propagation, that is which is known as the TEM mode of propagation, there will be no propagation of EM waves at all. Okay. So moving towards the next one, which is the TM mode of propagation, that is transverse magnetic mode of propagation. That is the transverse magnetic field. Transverse magnetic field exists, and the longitudinal magnetic field in this case, that is in TM mode of propagation, will definitely be 0. You can see here this result we discussed earlier. In these cases, if Ez equals to 0, then we call these waves as transverse electric waves, and if Bz equals to 0, we call these TM, that is transverse magnetic waves, and if both Ez and Bz both are 0, then we call them the TEM, that is transverse electric magnetic waves. Okay. So here we will discuss about the TM mode of propagation of EM waves. So in the TM mode of propagation of EM wave, there is no magnetic field components into the direction of propagation. There is no magnetic field component into the direction. If wave is propagating in this direction, then there will be no field component in this direction. That is, the longitudinal magnetic field is 0 in this case. So in the TEM mode of propagation, there is no magnetic field component into the direction of propagation of EM wave, but longitudinal electric field exists in this mode of propagation. So Bz equals to 0, but Ez does not equals to 0. As we see in the case of TEM waves, that Ez is 0 and Bz is 0, but in the TM mode of propagation, Bz is 0, but Ez does not equal to 0. So when you discuss this type of mode, we have a general solution for the electric field into the direction of propagation, that is Ez, which is a function of x and z, is equals to A sine beta x plus B cos beta x, because from equation number 10 and equation number 11, because Bz is 0, so this equation is not useful for us in this case, in this particular case, and we are left with only the considerable factor is only Ez, because Ez in this case, that is in this mode, is not equals to 0. That is, Ez is the only factor which is survive in this case. So here Ez is equals to A sine beta x plus B cos beta x, which is the solution of this type of differential equation, which is given by the equation number 9, and the solution of this type of differential equation is Ez, which is a function of x and z, is equals to A sine beta x plus B cos beta x. This. So on applying boundary conditions को अगर आप अप्लाई करें, ये बहुत ज़्यादा इम्पोर्टेंट है. ये जो बाउंड्री कंडीशंस हम यहाँ डिस्कस कर रहे हैं, इनके बारे में थोड़ा सा हमने पहले जब हम इस टॉपिक को स्टार्ट किया था, हमने बताया था कि एट द इनर वॉल ऑफ द waveguide, the parallel component of the electric field will be 0, and the longitude or the perpendicular component of the magnetic field will be 0. That is, the boundary condition is this, that the electric field parallel component will definitely be 0 at the inner wall, and the perpendicular component of the magnetic field will be 0. So this is the at the inner wall of the waveguide. This happened at the inner wall of the waveguide. So in this case, when we discuss about the TM mode of propagation, we are left only with Ez, that is the electric field longitudinal component, which is the solution of that differential equation a sin beta x plus b cos beta x. So the parallel component of electric field is definitely b equals to 0. So on applying boundary conditions, so boundary condition is here, you can see this figure. Boundaries are at x equal to 0 and the second boundary is x equal to a. These are the inner walls. This, see this. So this is the x equal to 0 and this is the x equal to a. So x equal to 0 is this and x equal to a is this. So boundaries are these two. These two are boundary conditions. So first we apply this boundary condition at x equal to 0, what happened, and finally we see that at x equal to a, what happened. So this. Now this. So on applying boundary condition at x equal to 0, at x equal to 0, Ez will be 0 because the parallel component of parallel component of electric field will be 0 at the boundary. This is the boundary condition. This. So Ez will be 0. If we put Ez in this equation, that Ez equals to 0 and at x equal to 0, so a sin beta into 0 and sin 0 gives you 0. So a into 0 plus b cos beta x equal to 0. So b beta into 0, that is 0, that is cos 0, and cos 0 gives you 1. So this equation, when at x equal to 0, Ez will be definitely 0, then you can get that Ez equals to 0 and a into 0 plus b into cos 0 is 1. So you can get this result, that is b is equals to 0 in this case. Okay, so b is equals to 0 in this case. So when you put b equals to 0 in this equation, you can get that Ez, which is a function of x and z, is equals to a sin beta x, because b is equals to 0, so this term will be 0. So Ez, which is a function of x and z, is equals to a sin beta x. Say this is equation number 12. Now applying the second boundary condition at x equal to a, Ez will be definitely 0, because at this inner wall, at x equal to 0, at this inner wall, E is equals to 0, that is the longitudinal factor Ez, because of this boundary, the parallel component. And what is the parallel component to the direction of propagation of EM waves is z, Ez. So Ez equal to 0 here, and this is the second boundary condition at x equal to a, so Ez will be definitely 0 at this boundary condition also. So this. So at x equal to a, Ez will be definitely 0. So this. So Ez equals to 0. If you put 0 in this equation number 12, so Ez equals to 0 and a is as it is because it is a constant, sin beta, and at x equal to a, put x equals to a here. So we are Ez is 0, a sin beta x replaced by a. So because a is a positive constant, so a does not equals to 0, then sin beta a, this factor, will definitely be equals to 0. And if sin beta a is equals to 0, then we know that sine in the angle of pi, where m can take any value, that is 0, 1, 2, 3, where m can take value 0, 1, 2, 3 up to this. So sine beta A is equals to 0, and 0 sine gives 0 value in this type of angle m pi, where m equals to 0, 1, 2, 3. Put here 0, sine 0, 0, 1, sine pi, 0 again, m equals to 2, sine 2 pi, so 2 pi is again 0. So sine beta A is equals to 0. So this angle, this type of angle, that is angle sine, when sine gives in this angle, when you put theta is equals to m pi, so this gives you always 0. So sine beta A is equals to sine m pi, and from this relation we can get that beta A is equals to m pi, and beta, from here beta is equals to m pi by A. So this is the result of this constant. This is the result of this constant beta is square, which is, we suppose this is equation number A, and this is omega by c whole square minus k square beta square. So the value of beta from this equation, from equation number this solution, we can get that beta equals to m pi by A. Okay. So on putting this result into equation number 12, in this equation we can get the result of the longitudinal electric field, that Ez, which is a function of x and z, is equals to A sine beta is equals to m pi by A, and x. So the longitudinal electric field is equals to A sine m pi x by A. And remember, if you once get the longitudinal electric and magnetic field, you can easily get the transverse electric and magnetic field by using equation number 7. By using this equation, if you get, once you get value of Ez and value of Bz, you can using these equation you can easily calculate the transverse electric and magnetic field components. So we here because we are discuss here the TM mode of propagation of EM waves or microwaves. So in TM mode of propagation, Bz, that is the longitudinal component of magnetic field, is always 0, and Ez is given by equation number 13, which is Ez equal to xz, which is a function of xz, is equals to A sine m pi x by A. So Bz equals to 0 and Ez equals to A sine m pi x. When you put these results into equation number 7, this equation, you can easily get the value of Ex, that is the transverse electric field into the direction of x-axis, transverse electric field again into the direction of y-axis, transverse magnetic field, and this is the transverse magnetic field into the direction of y-axis. So by putting these results into equation number 7, we can get the transverse fields, that is Ex equals to I beta Ka m pi by A cos m pi x equal to m pi x by A, and Ey is equals to 0. Why Ey equals to 0? See here, when you put Ey, iota over omega by c square whole square minus k square equals to k del Ez over del y. That means del over del y Ez, that is the partial differentiation of Ez, which is a function of x and z with respect to y. This, see here, yeah. This is the equation number 13, which gives you the value of Ez, which is a function of x and z, and is given by this this formula or this equation, a sine m pi x by a. And when you differentiating or partially differentiate this function with respect to y, then you can get that del over del y of Ez is equals to del over del y of Ez. What is Ez? Is a sine m pi x by a. So a sine m pi x by a, because a is a constant, so a del over del y sine of m pi x by a. And partially differentiating with respect to y of this function, which is a function of x, gives you 0. So the first term of equation number 7th, second, which gives you the transverse electric field in the direction of y-axis. So del Ez over del y is 0, and del Bz over del x, that is del over del x, or partially differentiation of Bz, because we consider the Tm mode of propagation. So Bz is already 0. So this function is 0 due to the partial differentiation, and Bz is already 0. So the whole factor, that is, this gives the value of Ey will be equal to 0. So from here we can say that Ex is equals to iota over beta k m pi a by cos m pi x by a, and Ey is equals to 0. And from here we can calculate the value of Bx, that is the transverse magnetic field into the direction of x-axis is equals to 0 in the same way by putting the value of Ez and Bz into the equation number 7, and By is equals to I omega m pi a by beta ac square cos m pi x by a. So this is the value. So overall we can see here that Bz equals to 0, Ez survives and is equals to a sine m pi x by a, Ex survive, which is equals to iota over beta k a m pi by a cos m pi x by a, and Ey is equals to 0. So Bz 0, Ez survive, Ex survive, Ey 0, and here Bx 0 and By survive. Okay, so the non-propagating mode. So the non-propagating mode is Tm0 mode, because the value of non-propagating mode is Tm, transverse magnetic 0. The value of m is equals to 0. So Bz 0, when you put m equals to 0, the non-propagating mode is when you put m equals to 0. M equals to 0. So when you put m equals to 0 here, put here m equals to 0, Bz is 0, put m equals to 0 in this function, you a sine m equals to 0, so sine 0, so Ez equals to 0, Ex, put m equals to 0, m equals to 0 here, gives you this whole function is 0, so Ex is 0, Ey is already 0, and Bx is already 0, and By is I omega m pi by beta ac square, put m equals to 0 here, so this function is 0. So when you put m equals to 0, this is called the non-propagating mode, and you can write it as Tm0 mode, and this is the method, that TMM mode, this TMM mode. So m equals to 0, that's why we can write this is Tm0 mode. So Bz equals to 0, Ez equals to 0, Ex equal to 0, Ey equals to 0, Bx equal to 0, and Py equals to 0 on putting m equals to 0. So this is the same result as we obtained for the TEM waves. This for the TEM waves, Ex equal to 0, Ey equal to 0, Bx equal to 0, By equal to 0, Ez is already 0, Bz is already 0. This is the same result as we obtained in the case of transverse magnetic mode. And propagating mode is already always the TMM mode when M have value greater than 1, and M value is always greater than 1. So this is a propagating mode when M has values greater than 1. M has value greater than 1, then By survives. M has value greater than 1, then definitely Ez survives, Ex survived. So this is the propagating mode. You can say that TMM, where M is always greater than 1, then this is the propagating modes, and non-propagating modes when M equals to 0. So students, that's all for now, and we will discuss the third mode of propagation of EM wave into our next lecture, next video lecture, that is the transverse electric mode of propagation of EM waves. Today we were discussing about the parallel plane waveguide, and in this lecture we were discussed about the TEM mode of propagation and TM mode of propagation. In the next lecture we will discuss about the TE mode, that is transverse electric mode of propagation. Thank you.